Hey everybody, in this lab we're looking to figure out what is the mass of one of these carts, but we're going to determine it experimentally. In the previous lab 5.1 you had to actually measure the mass of this cart in order to figure out the spring force that's accelerating it when we release the spring. So we know what the mass should be of one of these carts, about 500 grams or half a kilogram. In this lab we're going to pretend like we don't know what the mass of the cart is. We'll do an experiment and then using our knowledge of kinematics and the second law equation F equals ma, work back and calculate what the mass of this cart is. Let's take a look at our setup. Over here we have our cart. Right now it's upside down so it doesn't go flying down the track. You can see on the cart there is a paper clip and then a string. What happens is I'm going to flip over the cart when we're ready to go. And that'll be the setup. There'll be a string there to pull and accelerate the cart, and it will go flying down the track. There's a pulley at the other end, similar to a couple of these setups from the free body diagram stations that we did. And I'll show you what's at the other end of that. So right now at the other end we've got the pulley, which we're assuming the pulley is not offering any friction, pretending like it doesn't have any inertia. It's not going to affect the experiment. So the pulley is just there to redirect the direction of the string. At the bottom of the string, at the other end, we have this small mass. And because this track is pretty much frictionless, all it takes is a tiny amount of mass right here to accelerate the cart at the other end and make it come along the track, speeding up the whole way down. We're going to release the car from rest and figure out, just like we did in the previous lab, what its acceleration is. That's going to be something we need to find out. Since we need to determine the acceleration of the cart as the hanging weight accelerates it, I've marked a starting position and an ending position down there for where we'll observe the motion of the cart. We can analyze that distance or its displacement, delta x, along with the time. We'll have a timer running on the screen, and we can use that information as well as the knowledge that our initial velocity is going to be 0 to figure out the acceleration. You can see we have numbers on our track once again. This thing is directly lined up with 102 centimeters. So this is the starting position, 102 centimeters, or 1.02 meters. I've chosen an important ending position that is based on exactly where the hanging weight just touches the ground. Since we care about how the weight is accelerating the cart, then we're just going to analyze the motion of the cart over this distance that the weight accelerates it. So this is where the weight's going to be hitting the ground. That's going to be our final position and our final time. And that final position is what I've labeled as the ending position. So that's a measurement you'll need to take. There it is right there, 27 point something. And our starting position is over here, 102 centimeters flat. So find the difference between those two positions. That's your delta x. And even though the track's kind of backwards, you can just use that as a positive number. You don't need to call it a negative value. The other piece of information that we're going to need is some information about the hanging weight. So let me grab that. Last time when we needed to know the mass of the cart, we threw it on top of the triple beam balance. This hanging weight, however, has its mass already printed on it because it's a standard amount. Let's see if you can see it. Don't focus on me, camera. Focus on the thing. Aha! All right, so that's, you can see what number that is. And there's a little g, so this is in grams. All right, so there's the mass of our hanging weight that's going to be accelerating the cart. That's just the mass. You need to know the force that's pulling on this. Force of gravity, Fg, and weight are the same thing, identical. So if we want to know what Fg, or the force of gravity, is acting on this guy, we just need to take its mass in kilograms, not grams, but its mass in kilograms, and multiply it by little g. We'll use 9.8 meters per second squared because this is in reality. This is an actual lab. We're not going to round little g to 10. So the mass of this thing in kilograms, make sure you convert it, multiplied by 9.80 meters per second squared will give us the force of gravity in newtons pulling this thing downward. And this thing being pulled downward is what's going to be accelerating our whole system. The cart and this mass will both be accelerating. We are at our starting position. Based on where the camera is going to be, though, it's going to look like it's not, because that's what perspective does. Okay, but we are starting right here at our starting position. That's exactly where this cart is, right there. All right, to recap, we have the information about how far our cart traveled while it was being accelerated by the hanging weight. We should be able to see how much time that took for it to accelerate across that distance or displacement. We also have the mass of our hanging weight, which we can use to figure out what the force of gravity is pulling on that weight. Make sure anytime we're calculating newtons of force, you need to have mass in kilograms, and you should have acceleration in meters per second squared. Otherwise, you're going to get a value that's not actually in newtons. Remember, our objective is to figure out what is the mass of that green cart that's being accelerated along with the little hanging mass. Figure out the mass of the green cart, and we can compare that to the value we got in our previous lab. We know that it should be somewhere around 500 grams or 0.5 kilograms.